Hi, I'm John Doherty, and in this short video I want to talk about data space inversion. Now, I believe that data space inversion can be of tremendous use to decision support groundwater modeling. So, before I talk about data space inversion, I'm going to say a few words about decision support groundwater modeling, just to set the context. So, as decision support modelers, what's our job statement? Our job statement is to predict the future behaviour of a groundwater or environmental system, probably under a new management regime. And in making those predictions, I need to accompany those predictions with estimates of the uncertainty associated with those predictions. I do this for a few reasons. It gives decision makers and stakeholders an idea of the risks that are being taken. It's also an estimate of the credibility of the predictions made by the model. So, my task is to make predictions of management interest and accompany them with estimates of uncertainty. Now, the uncertainties could still be high, but my task is to reduce those uncertainties as much as, I can, as much as available data allows, and I do this through assimilating information from data that I have available. For some predictions, this will reduce the uncertainties considerably. For other predictions, maybe not so much. It depends on the information content of available data. So that's my job statement. For any job, there are metrics, and the same thing applies to decision support modeling. When I make a prediction and when I quantify its uncertainty, one thing I must not do is understate uncertainty. I mustn't give decision makers a false impression that they aren't taking risks. They need to know the risks they're taking. They need to know the credibility of the predictions made by the model. At the same time, while I mustn't understate uncertainty, I don't want to overstate uncertainty by too much either, because there's information contained in data, and it devalues data not to harvest that information in order to reduce the uncertainties of decisions we care about. So my metrics then are not to understate uncertainty, but not to overstate it by any more than I can help. And I do this by harvesting information from data and taking that information to the decision-making process, to the decisions, to reduce the uncertainty of the predictions that the model is making. So how do we translate this into a workflow in traditional decision support modeling? Well, first we build a model. It may be a complicated model. If the site is complex, if the processes are complex, the model may be complex. It may take a long time to run. It may be numerically unstable, but I build a model. And then I equip that model with parameters. Parameters are adjustable by definition. Parameters could be pilot points, they could be structural overlay parameters, they could be zones of piecewise constancy. But the important thing is to have enough parameters in that model so that I can fulfill the metrics that we just spoke about. I need to have more parameters than I can estimate uniquely. The parameters that I can't estimate are just as important as those that I can, because they may be the ones that lend uncertainty to the predictions I care about. So I've got to have as many parameters in this model as a prediction of management interest is sensitive to. So we build the model, equip it with parameters, and then equip those parameters with a prior probability distribution. Then, using for example the PES Ensemble Smoother or some other device, I take the prior and translate that. I change the parameters till from originally sampling the prior probability distribution, they're sampling the posterior parameter probability distribution. That is, they are history match constrained. That is, these parameters have absorbed the information that is contained in a history matching data set. Now I'm sampling the posterior parameter probability distribution. I make a prediction of management interest with all of these samples, and in doing so I quantify the posterior uncertainty of that prediction. So in doing this, I've harvested prediction relevant information, pointed it at the prediction, made a prediction, quantified the uncertainty of that prediction. In theory, it should all work. In practice, there are a lot of problems. Generally, this requires a lot of model runs. It requires that a model be well behaved, numerically stable. It requires that parameters be adjustable. And sometimes the things that affect predictions that we care about, they're uncertain but not necessarily adjustable. And another problem when we're using something like an ensemble smoother is that often the uncertainties that we get out of the ensemble smoothing process are really only indicative. They may be too high, for example, if I don't fit the calibration dataset very well. They may be too low if there's ensemble collapse. It sure is better than not quantifying uncertainty, but often the uncertainties that I get out of this process are good but not great. Which begs the question, is there a better way to do all this? A way that gives me predictive uncertainties and predictions that I can perhaps place a little better reliance on? And the answer is often yes, not always but often. And the way to do this is through implementing data space inversion. So let me describe the concepts behind data space inversion before describing some of the implementation details. Let's look at our traditional workflow again, but let's look at it this time from the point of view of flow of information. When we do things in the way I've just described, traditionally through parameter adjustment, information flows from data to parameters as they're adjusted. These become the receptacles for information provided by the model. Information then flows to the prediction that I care about. With data space inversion, things are different. Information flows directly from data, recorded measurements of past system behavior, to the future. The model is still important because we want this transfer of information to respect the physics, the chemistry of the system, all the processes that are operative in the system. But the model now is an enabling device that constructs the wherewithal for information to flow from here to here. The model is in fact used to build a statistical linkage between the measured past and the managed future. Once we've built this statistical relationship between what happened in the past and what's going to happen in the future, we can then use our field measurements to make predictions of future system behavior conditioned on those measurements. But we're not using the physically based physical numerical model anymore, we're using the statistical model in its place. And this has large advantages, especially in speed, which we'll talk about shortly. So, that's the concepts. Now look at implementation details. There are a couple of ways to do this. We look at option 1 first. Option 1 is generally not the preferred method, but often works well. But if our model is linear and complex, option 2 is often better. But option 1 is illuminating, and there are a lot of overlaps between option 1 and option 2. So, we start off with realizations of our parameters. So here is our model domain, and we're going to populate that model domain with, I'm going to pluck a number out of the air, say 300 realizations of the prior parameter probability distribution. But this is very liberating because these don't actually have to be parameters in the traditional sense. There may be a structure here which may or may not exist. There may be a alluvial channel here which may be here or there or nowhere at all. The parameters, the expressions of what may be under the ground, do not have to be adjustable when we're using data space inversion. And that is tremendously liberating. We don't have to adjust these representations of the prior to obtain representations of the posterior. We just have to represent anything that may exist under the ground in, for example, the 300 model runs that we initially do to set up our statistical model. So we populate our model 300, 400, 500 times with realizations of whatever may be under the ground, with all the complexity or possible complexity associated therewith. We run our model 300 times over the past and then into the future. Now let's just focus for the moment on one prediction, which I'm going to call little s. It's a scalar, and look at the uncertainty of this prediction. This could be a prediction of management interest. Now right now I've done enough model runs to characterize the prior uncertainty of that prediction. But it's not the prior I'm most interested in, it's the posterior uncertainty of that prediction. And to obtain the posterior uncertainty of that prediction, I have to harvest information from measurements of past system behavior. Let me suppose that these populate a vector h, and that they're the red dots in this column. So there are my measurements of past system behavior, and for each of the model runs that I've done based on each of these parameter fields, I have model generated counterparts to these measurements. These are the blue dots. Now let's put the model aside. We've done 300 model runs, 300 runs of that model, which may be big and complex. That's all the model runs that I need to do. So let's just focus on what I've got here. And for the moment, let's just put the observations, the field observations aside. So now we've got the model generated counterparts to field observations, and we've got a prediction that we're interested in. Now I'm going to add a little bit of measurement noise to these model generated observations, because the uncertainty of any prediction has to take account of the fact that measurements of past system behavior are somewhat contaminated by measurement noise. So I use noise enhanced model outputs. Optionally, I can undertake a normal score transformation so that each of these outputs is actually Gaussian on its own. And then, and this is the important bit, the hard bit, but it's really the easy bit, now I'm going to construct a covariance matrix that links the past to the future using model outputs of both. Complementary to these model generated measurements is this prediction, etc. So I have the ability to build up a correlation structure between what happened then and what will happen in the future. And I'll also take the means of these quantities individually. So I want to build up a mean vector of each model output and the prediction, and a covariance matrix, an empirical covariance matrix that links the past to the future. Now, building a covariance matrix is easy. We learned how to do that back at school. There's standard statistical formulas that allow us to construct an empirical covariance matrix based on measurements. And you're all familiar with these formulas. And here I've just partitioned this covariance matrix, separating future from past. These are the cross-covariance terms here. So construction of the mean vector, construction of this covariance matrix is easy. Once I've done that, I've taken my statistical linkages between the past and the future, these empirical linkages, and described them by something that has statistical currency, the mean values, the empirical covariance matrix. Now let me reintroduce the observations that were made in the past, these red dots. And now I ask, given these observations, what's the expected value of the prediction that I care about? And what's its uncertainty? Well, this can be easily calculated. I just condition my statistical model by the measurements that I made in the field, and using formulas that are well known in statistics and linear algebra, I then have the expected value of the prediction and the uncertainty of these predictions. Now, we're assuming here a Gaussian relationship between the past and the future. The fact that the model is nonlinear and that relationship probably isn't Gaussian is somewhat but not entirely accommodated by the fact that I've done normal score transformation. So these predictions, the value of this prediction and the value of the uncertainty, are normally pretty good. If you're using the PES suite, this is all easily done using programs DSI and DSI1. If you're using PES++ and PyEmu, there's other functionality available to do the same thing. So, this works well. The numerical burden is only those 300 model runs that I did at the beginning. The rest is numerically trivial. So, it works well. But it doesn't work well all the time. If the relationship between the past and the future is too nonlinear, then I need to go to a little bit more trouble to ensure that the conditioning process is a little bit better approximation to Gaussian, that I can apply Gaussian concepts to a more nonlinear process. And to do that, we use option 2, which is similar to option 1, but different in a couple of important respects. So, let's have a look at option 2. We start off the same way as we did for option 1. We run the model 300 however many times with our parameter fields of arbitrary complexity. We run the model over the past and into the future. Now let's focus on a few predictions which we encapsulate in this vector S. So focusing just on the predictions. As before, we have measurements of past system behavior encapsulated in a vector H. And we can identify the model-generated counterparts to these measurements. Let's throw away the model now. Let's throw away those measurements just for a while. Let's concentrate on the relationship between the measured past and the managed future. Once again, optionally, I can do normal score transformation of each of these outputs and each of these predictions to help me approach Gaussianality. And then, as before, I get the mean of each of these outputs and each of these predictions, and I build an empirical covariance matrix which links the measured past to the managed future using these same standard statistical relationships. But now things become a little bit different. I've built up my covariance matrix. There it is, my covariance matrix that links the past to the future. Partitioned here, future, past, cross-covariance terms. I subject that covariance matrix to singular value decomposition, that is, principal component analysis. And in so doing, I obtain this orthonormal matrix V and the diagonal matrix S. Then I take the square root of that matrix. Now, the square root of a positive semi-definite matrix is a matrix such that if I multiply the matrix by its transpose, I regain the original matrix. And then I build a surrogate model. And this is a statistical model, but it's a little bit like a numerical model because it's got parameters. The parameters are x. And the prior probability distribution of these parameters is the identity matrix I. Each of the elements of X are independent, normal, standard deviates, Gaussian deviates, mean of 0, standard deviation of 1. And it can be shown easily that if I generate random realizations of X using that covariance matrix, the statistical relationship between O and S is exactly the same as for the big complex model. So I don't have to calibrate the big complex model. I can calibrate this model instead and then make predictions with calibration constrained realizations of x. I can condition x and make my predictions with samples of the posterior distribution of the parameters x. Now the time it takes for this model to run is a fraction of a second. But the thing about this model, even though it's a statistical model, it is a numerical encapsulation, a parameterized encapsulation of linkage between the measured past and the managed future. It is a model that replaces this statistical distribution. And then when I'm conditioning the prediction against the measured past, I history match this model instead of the big one. So now I bring my measurements back into play and I history match this little model, and once I've done that I can make predictions with this little model, this statistical model, quantify their uncertainty and get the most likely values for the predictions. So how do I history match this simple little statistical model? There are a couple of options here. Both of them are exceptionally easy and extremely numerically fast. Option 1 is simply use PES. Sample the posterior distribution, probability distribution of x, and hence of the predictions that are made using x. I then obtain the posterior probability distribution of the prediction and including the most likely value of the prediction. That's option 1, trivial because this statistical model runs so quickly. Option 2, which is slightly better in some circumstances, particularly if the relationship between the past and the future is somewhat nonlinear, and if I'm interested in time series in the future, I can calibrate that simple statistical model using Tikhonov regularization and PEST-HP to get the most likely value of the prediction, and using a little post-processor that comes with the PEST suite, I can automatically obtain the confidence interval of that prediction at a number of confidence levels. And this works really well, particularly if there's a time series outputs. It avoids having non-physical behavior of time series outputs. So these are my two options. Either works fine on most occasions, either is extremely smart, extremely quick. Both give good estimates of the prediction of future system behavior. Both give good estimates of the uncertainties associated with those predictions, and the numerical cost really is only the cost of the 300 big model runs that were used to set up the statistical model in the first place. The rest is numerically trivial. Either option can be set up using the DSI2 utility that comes with PEST. Similar functionality is available through the PEST++ and PyEmu suites. So to conclude this video, let's summarize the benefits and the drawbacks of DSI. The most obvious benefit is its extreme numerical efficiency. You only need a few hundred runs of the model. So that model can be very complicated, it can be slow running, but you only need a few hundred runs. You are not using that model as a basis for parameter adjustment. It's only used, these 300 model runs, they're only used to construct the statistical model that enables information transfer between the measured past and the model future. And it's not either or. So you don't have to make a choice. Will I use PES/PIES or will I use DSI? You can use both. If you're using PES/PIES, you are undertaking lots of model runs based on realizations of prior parameter probability distributions. You have model generated counterparts to field measurements. If you run the model into the future as well using those same realizations, you can undertake DSI, and then you can check the uncertainty intervals and the predictions that you make with PES/PIES. The third benefit is that, as I mentioned previously, parameter fields can be of arbitrary complexity. They can be categorical. They can involve structural or alluvial or geological geobodies that may or may not exist, have certain shapes or other shapes. They do not have to be adjusted. They just have to be represented in some of the realizations that are used as a basis for construction of the statistical model. And then with DSI we can accommodate uncertainty in the uncertainty. Often we're not exactly sure what the prior parameter probability distribution is, so we can introduce so-called hyperparameters that govern the shape of the prior parameter probability distribution. So then selection of a parameter field becomes a two-step process. Firstly, we sample a random realization of the hyperparameters that governs the nature of the prior parameter probability distribution, and then secondly, we select parameters using that distribution. So we can accommodate the full range of our knowledge and lack of knowledge of what exists under the ground. And finally, DSI can be used for analyzing the worth of existing and contemplated data. We can construct a statistical linkage between the measured past and the managed future, but that measured past or the managed present, the measurements that we're using to construct that statistical linkage don't actually have to exist. We can pretend we have those measurements, and we can see how much the uncertainty of decision-critical model predictions is reduced if we had those measurements. Therefore, we can inquire into the ability of different types of data to reduce the uncertainties of predictions that we care about. The whole process is non-linear. There's no linearity assumption here. And it can be undertaken very quickly because of how quick the conditioning of the statistical model can take place using either of options 1 and 2 that we just described. Drawbacks? Well, of course there are drawbacks. Something this efficient, there's got to be a price to be paid somewhere. But in my experience, the price often isn't too much. If the relationship between the past and the future is dreadfully non-linear, then this isn't going to work. But then again, other methods such as PES/PIES will also be challenged too if information has to flow from the past through parameters to the future. So there's going to be problems either way. DSI will often perform stunningly well at very small numerical cost. A conceptual problem is that you get to see the posterior probability distribution of predictions that you care about, but you don't get to link parameter fields to those predictions. And this can be a concern particularly for pessimistic predictions. It is nice to see the parameter fields that are responsible for things going wrong in the future. And finally, it's important that the model be complex enough so that relationship that we build up between the managed past and the measured future has integrity. The statistical model that we construct will then itself have integrity, and the predictions that we make and the uncertainties that we quantify will have integrity. If the model is too simple, these relationships are false, and the statistical model is, well, it's defective and it won't work. So That's it really. That's a fairly brief summary of data space inversion. Thank you for listening.